as close to reality as possible. And of course, any generated surface will necessarily have to be an idealization of that. However, the measured surface will also have uncontrollable features and also high uncertainty. So, for example, if you see this blue surface here on the left, that's a measured one, and this is a very nice measurement actually. But still, you see all these high dots in yellow that might be inclusions, might be some measurement artifacts. I'm not sure really, but that will surely complicate the analysis. And on top of that, they might be expensive to obtain because, of course, I mean, you need to manufacture the surfaces and then measure them. On the other side, you have a very nice, very smooth, very artifact-free generated surface. And that's the main advantage of a generated surface, that it's controlled. If you do it correctly, you can control the uncertainty, and they are readily available. So what that means is that while it is very hard to do parametric studies on measured surfaces, it is much more easy to do it in generated one. And therefore, a very fruitful approach that many researchers had followed in and only once the pattern is well established, then you go and you measure the surfaces and you check that for your particular surfaces, then your this pattern also holds. But of course, for this to be adequate, what has to happen is that the generated surface is as close as possible as the measured surface. And the question is, what do we mean by as close as possible? So let me try to do it or to explain it. We talk about how do we describe a surface, especially in an industrial setting. The most common pattern or the most common parameter used is either RQ or RA. Both are actually quite similar, and they are giving a more or less a sense of how large is the roughness. So basically, if you see these lines here, those are these dashed lines are the values of RQ and RA, and basically what they are telling is an average height. But of course, anyone that has worked in the field knows that this is not enough. And why? Well, we have these three profiles now, and they all have the same RQ, but of course they are looking extremely different. And say if we would say that they have the same RQ, therefore they are the same, we would be completely misled. So we need a different parameter. And a very common one is this skewness parameter, which is computed in this fashion as the third power of the height difference. And basically, if you have a positive skewness, you will have more peaks than valleys. If you have a negative one, you will have more valleys than peaks. And if you have a 0-1, you will have a more or less average or sort of evenly distributed peaks and valleys. But of course, two parameters are not enough either. And again, we can have these two profiles that they have the same RQ, they have the same skewness, but they still look quite different. The one on the top has this one massive, very high peak, whereas the other one is having a lot of these much smaller peaks. And of course, you can think that this is also going to affect the performance, because, for example, if we talk about contact, here the one on top is gonna contact only on the on this very high peak, while the other one is gonna contact very quickly on a different number of peaks. So again, what we can do is to is to create more parameters. And so, for example, we have kurtosis, which is the fourth order momentum, which is the fourth order moment. And of course, we could proceed with the same story, but you know where it goes. We could go and say the fifth order moment, the sixth order moment, and so on. But eventually, this starts to become pointless because, well, it's harder and harder to assign a physical meaning to all these higher order parameters. So for the skewness, it was very easy, amount of peaks, amount of valleys, and so on. For the kurtosis, some attempts have been done, but they are a bit less reliable, and very few correlations have been found with it. For higher order moments, not even that. So what can be the alternative? Well, we can go and look at the high probability density. High probability density is actually very related, almost the same as the Abbott's curve that Andreas was talking before. And basically, we define it as we define it according to the area. So this area in red that I'm marking on the high probability density, that indicates that's a probability that the height is between those two markers. So basically, that means if I go to the profile and look at the portion of the profile that is between this height range, then this sort of not this is the length, but the proportion of the length will be equal to this area here. And of course, if you can, you can clearly see that this contains a lot more information, and in particular, it contains all the information about the skewness, about the RQ, and all the previous ones that we have combined. But of course, it also has much more because it also includes all these other higher order moments. And here we can see those two profiles that before we said had the same skewness, but still were different. Now, if we look at the high probability density, it's clear that they have a very different high probability density, and in particular, we have this higher this high part here that denotes this sort of deeper valleys and so on, and also here these high peaks are quite different. So with that, we have characterized the height of our surface in full detail. However, again, this is still not enough because we also need some lateral information. So again, I'm showing a couple of profiles, and these two have the same high probability distribution. So same RQ, same skewness, same kurtosis, same and all higher order moments. But still, they are looking quite different. So the first one, somewhat smoother. The second one is a lot more a lot more rugged, and that tells us that probably we need some information about how, say, some lateral information. And now if we look at this lateral information, the equivalent to the high probability density is the power spectral density. The power spectral density is going to give us all the information, all the lateral information that we might need about the surface. So for those that don't know what it is, we can start by looking at the power spectral density of a sinusoidal wave, and then we understand that it's basically telling us the amplitude and the wavelength of this wave. So we have the wave number on the x-axis, and that's defined as q equals to 2 pi over lambda, where lambda is the wavelength. So for example, in this case, we have 1 millimeter and we have 8 waves on it. So the wavelength would be 1 millimeter divided by 8. So if we plug in, we have a wave number of 5 to the 4. And that's exactly what the x-axis is marking. On the y-axis, we have the power spectrum, and that's marking the square of the amplitude. So the amplitude here is 10 to the minus 6. So if we square it, we get, say, 10 to the minus 12. If we look at a real profile, not a simple sinusoidal, not a simple sinusoidal wave, then what we see is that the power spectrum is actually a lot more complicated, and it has this more or less this complex shape. But we can still interpret it as the same as before. So basically, the power spectral density is given by the square of the Fourier transform. So basically, what it's doing, it's taking the profile, it's splitting it into many sinusoidal waves at different wavelengths, and then for each of them, it's giving the square of the amplitude, and that's what's being plotted, and that's what the power spectrum density is. And we will see that for the algorithm, it's actually more convenient to work with the square root of the power spectral density, so just with the absolute value of the Fourier transform. And that's basically because in this way we skip squaring and taking the square roots all the time. So at this point, in order to finalize this discussion about the power spectral density, it is convenient to talk about self-affine surfaces. And this description comes from the observation that as we keep zooming in, we see ever more rough details. So say we are having this at this macro level in this larger domain, and we see a certain roughness, but we look at a peak and we might say, okay, this peak is now smooth, but not really. If we zoom in, we see that this peak is actually also quite rough. And even at this scale, we can say, okay, but now this peak is quite smooth. But again, that's not the case. If we zoom in again, we see that there is more roughness. And the observation is that in most cases, these smaller scales actually look the same as the larger ones. And they of course look the same when we do the appropriate scaling. But still, more or less, if we scale them in the same manner, we could not distinguish this very fine detail with the, say, more microscopic roughness. And then a common way to study these kind of surfaces is to define them as a self-affine. And these have a very simple power spectrum, which is just given by a power of the wave number. So the wave number raised to -2 and 1 plus h, where h is a power spectrum. Has to be taken into account, however, that this power spectrum or this equation here is better understood in an average sense. So if you take the power spectrum of a real surface, of a measured surface, it would have a power spectrum as marked by these dotted, by these orange dots, that they are a bit all over the place. However, if you take the average of these dots, it will come down to this nice straight blue line. Yeah. And finally, another important feature of this power spectrum is that in general we will only consider the surface to be self-affine between two ranges. So we have Q0 defined as 2 pi over lambda 0, and lambda 0 is the longest wavelength present. So of course, if we measure a surface at say 1 millimeter by 1 millimeter, the longest wavelength that might be present is again 1 millimeter, because otherwise you could not have measured it. But quite often it is convenient to sort of filter out this waviness and take a roughness that have wavelengths that are smaller, say 0.2 millimeters instead of 1 millimeter. And then we also have this high cutoff Q1, which is defined as 2 pi over lambda 1, and this indicates the shortest wavelength present. In a real surface, this usually goes to the atomic scale. But in any numerical computation that you want to do, because of grid size, you will always have to cut it at some point. So lambda 1 here will indicate this point where you have cut it, and you have no more wavelengths present. And of course, in the previous, what was being plotted was more related to a profile. Here we will discuss with surfaces, and in surfaces we define the power spectrum in exactly the same manner. It's just that now we have the wave number goes in x and y direction, and basically this plot is showing exactly the same, just that it's a bit more complicated to see. So you see this yellow part here is the part where the power spectrum follows this power law, and then this blue part is where it has been set to 0. So for example, this, say, around 30 is the highest wave number present, and all the rest is basically zeros. Of course, numerically, it's not really 0, just a very small number, but still, it's important to consider that. And of course, and the model is, and the algorithm that we will present is perfectly capable. We could here consider also anisotropy and so on. And we will not consider it today for time constraints, but the algorithm is perfectly capable of handling it. And so, what is a traditional approach? Well, we take a self-affine power spectrum, we take a Gaussian height probability density, and we compute our resulting surface. And this is very simple to obtain, and this is the most common. For example, the quantum mechanics challenge was using this type of surfaces, and in general, say 90% of the papers dealing with this sort of generated surfaces will work with Gaussian surfaces. And of course, there are two reasons for that. One, it is very simple to obtain, but two, and more important, there are many processes that generate Gaussian surfaces. In particular, those that are those in which the surfaces are generated by a lot of very small events. So, for example, grinding, sandblasting, a fracture would generate all Gaussian surfaces. But then there is, of course, many other processes, say turning, say additive manufacturing, and so on, that will not result in a Gaussian surface. And that's why we want to study also other types of surfaces. And just to give an example of the importance of considering these non-Gaussian surfaces, let me introduce the Weibull distribution. The mathematical formula is not so relevant. The important part, as you see, basically, the smaller this p parameter is, the sharper this fall on the left is. And also, it's also important to see that the difference with the Gaussian is really not that huge, as it's seen in the drawing. So we're not going to a very extreme case, but still you will see that it's relevant to consider. And so what we do is basically the same. Take a self-affine power spectrum, we take a Weibull distribution, and with the algorithm we will present today, we compute the surface. And now you can see that because of this very sharp fall, you have all these peaks more or less at the same color. So basically you have all these flat peaks. So for example, to conceptualize it, this could reflect a more or less worn surface where initially it was Gaussian, but the peaks have been flattened out. But okay, now we can generate it directly. We can study it. And these results, they come from a paper that Andreas and I also wrote in 2021. But this is just an example. And that shows the stiffness as a function of load for a Gaussian surface in purple, and for 3 surfaces with a Weibull distribution. And you can see that the stiffness here is actually quite different. So it might not look all that different in the graph, but do note that the stiffness is so the y-axis is in logarithmic scales. So actually the differences are pretty notable, and in quite some times if they are of more than 1 order of magnitude. So that justifies the need for getting not necessarily a Weibull distribution, but a Weibull distribution that is as close as possible to the surfaces we want to study. And of course, this relates to stiffness, but similar results will be found with contact area and other properties. Okay, so with that very long motivation about the method, let's go directly to the let's go finally to the algorithm. And basically, this algorithm is taking a power spectrum, is taking a height distribution, blending them together with some tolerances, and is spitting out a surface. So in general, how does it work? Well, we first normalize the inputs. I'll explain why now. And then we basically iterate between this cycle. We correct the power spectrum, we correct the height distribution, then we check the error. And if it's small enough, we're done. Otherwise, we circulate. So we start by the normalization. This we basically have to do because both the power spectrum and the height probability distribution encode the mean value of the height and also the RQ value. And therefore they must be equal, otherwise we would run into trouble. And the normalization of both does ensure that this happens. Of course, once you have once you have the generated surface, you can undo this normalization to get the mean value and the RQ value that you desire. And so, going to the meat. So we start by correcting the power spectrum. So we start usually with high distribution that we have inputted. That might be, for example, random noise. It might be white noise. And then if we take the Fourier transform of that, we set that the absolute value is what we defined as the square root of the power spectrum, and the phase is somewhat related to the height probability distribution, but it's not directly related. So what we want to do is to only change the modulus. So for that, what we do is we divide by the modulus and multiply it by the desired power spectrum. And by that, we have a surface that has the desired power spectrum, but now we have distorted the height probability distribution. By the way, if you would be generating a Gaussian surface, that's all the steps you need to do. The Gaussian distribution is the only one that is not distorted by this approach, so you will be ready. If you are working with a distribution different than a Gaussian, then you have to proceed and correct the height distribution. And here, what we want to do is to change the height distribution, but at the same time minimize the total change in the surface. So for that, what we do is we start by sorting our surface in order. So we have these Z values that represent the surface. Of course, it's a very small profile, but it's good for the example. And we order them. So now that Z1 is the highest, then comes Z5, then Z2, then Z4, and so on. And then we also have H sorted, and H is containing these points with the right probability, with the right height probability density. And then what we do is to start pairing all these values. So we pair the first one with the first one. Now it's Z1 paired with H1, and therefore we substitute Z1 by H1. Then we do the same with the second in line. So in this case, H2 is paired with Z5, and then we substitute Z5 by H2. Then we continue. H3 is paired with Z2, so Z2 is replaced by H3. And so on. We continue until we have paired all of them. And in this manner, we have changed the height. Now the height distribution is perfect. However, the power spectrum is now probably modified. and therefore we need to compute the error. And to do that, we compute first the error in the height distribution. And basically, if we have ZH with the perfect height distribution and ZP with the right power spectrum but the wrong height distribution, what we can do is construct a histogram of both by dividing the height in some bins and placing how many points fall in each case, and therefore we can study the difference between these two these two histograms, and we add all these differences together, and that's what we call the error in H. But then we can also compute the error in the power spectrum, and for that we basically use the RMS value of the relative error. If you see here, that's the power spectrum, basically using it's the square root of the surface with the perfect height distribution minus the one with the perfect power spectrum and divided by the perfect power spectrum. And we compute that, and that's our error in P. But of course, notice here that in these points where the power spectrum is supposed to be 0, it's not very smart to do the same, because here we probably would have very relative errors just by the fact that we're dividing by 0. So instead, what we do here is we compute the normalized value. We compute the normalized RMS value of all the points that should be 0, and that we assign as RP0. And of course, that if that is small enough, then we know that everything we wanted to be 0 is actually 0. And so with that, we can now check the exit conditions, and basically in the algorithm we will share there are three options. First, that the ideal one is that convergence is reached. So that means that either the error in H is smaller than a tolerance, or the error in P, or in the power spectrum, is smaller than the tolerance. Of course, we only need one of them, because there is always one surface that has either the perfect height or the perfect power spectrum. However, that's not always the case. Sometimes we need to stop because of a slow speed, and that happens when the surface is not changing anymore, but the error is not smaller than the tolerance. So in this case, we also stop the code. And finally, if the algorithm has failed, which rarely happens, the maximum number of iterations is also used as a criterion to stop. And that's basically all there is about the algorithm. And so with that, we can now generate all these surfaces. And these, for example, are some of the examples that we presented in the article I was saying before. But of course, if you go there, you will find more examples. So, for example, here you see three different Weibull distributions. One very close to a Gaussian, and then departing from it more and more. And you can see how the tops become flatter and flatter, and that's exactly what we expected. And then we can also do the same with the power spectral density. So as we go down Hertz exponent, we see that the detail, that the amount of detail that we see is greater and greater. So at 0.8, things are more or less smooth. At 0.3, you have all this high level of detail. And yeah, let me just comment on that the error, as I said, it does flatten out after a while, and you cannot achieve a smaller error than that. But usually, the error attainable becomes smaller as the number of points in the surface becomes bigger, and that's basically because we're giving the algorithm more flexibility. But even for normal surfaces, the errors are in the order of 1%, which is for most purposes quite a good option. And let me finish this presentation with just a small caution, and that is that in some occasions this algorithm is giving artifacts. So, for example, if you see this in this surface, you see this point with all these ripples around, and this, of course, is not real. But actually, as I will argue now, this is not really a fault of the model, but a fault of the inputs. And let me try to justify that. So say that I have a surface that I generate two Gaussian surfaces with the traditional method, not with our algorithm. And this I generate with lambda 0, so the largest wavelength is equal to L. So in this case, is equal to the whole domain. If I do that, then I see that these two realizations actually have this high distribution that is in gray, and they deviate quite a lot from a Gaussian distribution. And that's because you should not interpret these two generated surfaces as a surface with a perfect Gaussian distribution, but more of I have a very large surface with a Gaussian distribution, and I pick a small sample from it. Of course, if I pick a small sample, it doesn't necessarily have the exact same distribution as original. However, you would expect that if you take the combined high probability distribution of these two of these surfaces, they will converge to the Gaussian. Well, it doesn't for 2. 2 is a very small number, but if I go to 10, they do start to converge. And if I go to 100, they're even closer. But of course, notice all these very large spreads on the gray distributions. So each of them, each individual realization has a high probability density that's very far away from a Gaussian, but the combination is very close, because we're basically having these very large Gaussian surfaces, and we're picking different, and we're picking small patches out of them. Of course, if these patches are larger, and that we can exemplify by taking lambda equals to L halves, in this case, the convergence is much quicker, and the individual realizations are much closer to a Gaussian. If we even go to lambda 0 equals L over 4, even individual realizations are starting to be very close to a Gaussian. And in general, in the literature, you are told that taking L over 8 or even L over 16 would guarantee that you have a perfectly Gaussian surface. Okay, now what's the problem? Let me go back. Yeah, these are the two surfaces that we generated with the traditional Gaussian method. And we generated with our method, we basically have this surface, which is pretty different, and actually has this artifact in the form of this very high peak. And the problem here is that the algorithm is too powerful. So if I plot the power spectrum of this surface that's generated with the algorithm, it perfectly lines with the Gaussian distribution. And so that's what I meant, that it's not that the algorithm is wrong, because really it's generating what you asked for. It has the right power spectrum, and it has the right high probability distribution. It's just that what we meant by a Gaussian surface is not this. What we meant by a Gaussian surface is this, where we have a very large Gaussian surface and select the sample. Here we have a very small surface that is directly Gaussian. And that's why you have to be careful. So what's the recommendation? Well, basically, you take lambda 0 as small as possible, and take lambda 1 as equal to delta x, where delta x is the grid size. Then, if you need, you can low pass filter to increase to increase lambda 1, and you can also select a smaller sample if you want. And if you take these two precautions, then the model is not going to cause problems. So to summarize what I said, we've seen that generated surfaces can be very powerful tool to study the effect of roughness, and that these, of course, can be even more useful if they can be generated in a flexible manner, controlling both the power spectrum and the head probability distribution, so that they can be as close as possible as the real measured surface. And we have presented an algorithm that precisely achieves that. And with that, I will leave the floor to Andreas.
Okay, thank you, Francesc. So I guess you now have made me in charge of the slides. Have you? Yep.
Yeah, you should.
Okay, thanks. Yeah, so now comes to the part, the easy part of this is just to download and try to make use of the tool, and I will give you some insights. So you see here at the slide, if you follow this link, you will find the app. And perhaps I should share my whole screen so you can see what I'm doing. Perhaps it's much easier. So I'll try to do that. I share whole my screen. So I just follow that link, came to the MATLAB File Central, and then what I need to do is to download this this app, this package. Probably you can, if you like, you can download the toolbox, but I say you should download the zip file, because then you're sure that you get all the files which you later can dig into and make use of and tailor things that you yourself like. So having downloaded that zip file, it's just to unzip it. I mean, you have this recipe, and this recipe, so you can really follow this recipe if you miss any bits and pieces now. But you unzip your file, and it ends up somewhere. Now you see I have done this before, so I have a number being behind it. I don't know if MATLAB likes that, so I just put an underscore or something. So now I have my folder, and what I need to do in this one is to locate this my surfgen app ml app install file and run it. And I had of course already installed it, but I reinstalled it, doesn't matter. And then typically when you are in your MATLAB, you are in your home tab, on your home tab, but you can find this app on your app tab then. And I don't know which view you like, but I could see it already from the first view, but here you can see it also. So if you click that, you get the tool. And now this is just a very simple app. It's easy to use, but it's still not perfectly explanatory. So you have things that you of course immediately recognize. So you have a Gaussian switch button, you have a bi-Gaussian and a variable switch button for the high probability density, and for the PSD you can select either a self-affine or an exponential one. But then you have the Hurst exponent, and if you don't know, I mean, what the Hurst exponent is, perhaps you need to read in our article, but the easy thing here is just to say it's the decay, how the amplitude of each wave, Fourier wave decays. And then Francesc talked about the anisotropy ratio, or if we could generate anything but isotropic surfaces, and yes, we can. And if you make this number larger than 1, you or transversal, and if you make it a lot smaller than 1, you get the other one. So you can generate surfaces whichever way you like, but of course you can generate one of them and then just transpose the results in your matrix. Here you put the high frequency cutoff, the roll-off frequency. So this is the lambda corresponding to lambda 0, but in terms of wave numbers. So you see that it's L half here. It's put 0.5 is one. I mean, we now randomize surfaces between which are in lateral size between 0 and 1, and then you can scale them to whatever you like. And then you key in the nodes, and then you can just press generate. And it comes like this to begin with. And now as you see what Francesco was telling about the algorithm, of course, now this surface, I mean, if you really nice, when you view this, if you're not so critical, you can believe it's a Gaussian surface. But of course, you may need higher number of nodes to get closer, and also a smaller role of frequency. And you can, the app is, I mean, this is very simplistic, so you cannot do so much. You can generate your surfaces, and then you can save your surface to a file. And what that does actually is just to let you save the results as an X, Y, Z triplet. Oh, and now something wrong. This is probably because because I have an overlap of my apps. But your app, which you download, it should do this fine. Otherwise, you would find in the directory where you had it, where you have unzipped it, you should find already an M file of the realist. Well, perhaps you don't. Perhaps we remove that just to not keep too much storage space. But here you can see, you can find them. You can find these files in the directory where you installed your app, and you can generate. However, so now I mean, this is perhaps it's a good visualization. What can the algorithm do? You can randomize surfaces like this, but of course, very quickly you want to do more, and then you go back to this directory, and you actually you have to browse there in your MATLAB. In your MATLAB window. So it's my surf, let's see. Where am I now? Documents, downloads. I should be here. Why? Because what I want to show you is that you can, yeah. Now I'm here. Hopefully now I'm in the right directory. And when I'm in the right directory, I can also open this MATLAB tool, the designer for the app. And here you can do, I mean, here you can add features and make your own app if you like. You can also check, for example, if you look the generate button here, what is the code text? What does it do when you press generate? So you can go to the code there, and this just only opens the code which you also can find in your directory. But here you can see what it does, and perhaps it's a little bit clouded by this MATLAB GUI coding, but it should be some instances should at least be quite easily discerned. And now we come to the heart of this algorithm, because it sits here. So this is what it input is just placed into the main surface generator function, which of course is found here, the main SG function. And then you can, I mean, having this code, now you can start to parameterize. You can run your own, you can create your own input arguments here, and you can randomize surfaces in a stack, different vary parameters, whatever you like. So I think this is very useful. And also here, I saw a question in the chat from Ida, I believe, and here you can of course also specify not only the Weibull, the Gaussian or bi-Gaussian height probability, or you can read it instead from a measured surface file. So if you, if you tailor this system, you can go to your whatever type of device you have to record a surface, the topography of a surface, and then you can feed it in as input here, extract the height, because you have all the functions to extract what you need, the height probability and so on. So everything is here, and then you can extract that, and you can start to generate surfaces exactly as you want. One more small thing here is that could be convenient. It's just a file which computes quite a lot of different surface parameters for any surface, which you pose as an XYZ triplet, like in MATLAB, where you have these mesh grid type of arrays. So perhaps that could be useful for someone of you. But this gives you some freedom to create whatever you need out of this type of yeah.
Wow, thanks a lot, Andreas and Francesc. Outstanding. I was even able to follow. So that's when you two give a presentation, it's not usually the case. So thanks for bringing it down to people like me. And yeah, it sounds pretty useful actually. Well, just to remind everyone that, because we got this question in the chat, the recording of this presentation will be available at tribonet.org if Andreas and Francesc give us their permission. No pressure.
Yeah.
Okay.
Yeah, that's fine. What we can do is also we can provide you with the slides themselves if someone wants to scroll through that.
Oh, that would be really great, actually.
It is. I can appreciate having that opportunity too.
Please, just I think I speak in the name of all of us. Keep going. If you keep bringing them on, we love these applications and these tools, and it's really great that you make them available, for free and in such a humble way or easy manner. So, thank you for that.
And also, what we look forward to, I and Francesc now, is to see how you make use of it, and perhaps you make very interesting modifications and further this work, because it definitely can be further.
Yeah, exactly. I mean, this you can say this code is just the beginning of it. Now it's just exploring all the possibilities with these more complicated surfaces and how they behave and so on. That's probably work for the whole community, not just for a couple of people.
Challenge accepted. Yeah. It would be great if we could run another webinar showing you what the community, what us were able to do with that.
Mm-hmm.
And if we find some bugs, we'll let you know.
Yes.
Well, I have to say that some people has already contacted and asked. So.
Cool. Okay.
In the app that Andreas uploaded, any error was already corrected. So hopefully now it works fine and perfectly.
I tried to run. I could run it, so it worked for me.
Could you also confirm whether you could save the file without running into the same trouble as I did?
Oh, that I didn't check actually. Let me just do it quickly.
Right.
Can you share your screen either?
Yeah, I can share my screen, but I already checked. It worked.
Okay.
You're fast. Good.
Yeah.
Fantastic. Yeah, because I that routine, the error I had, that routine should be skipped. It should be implemented directly in the code.
We have a question coming in, and you have 2 minutes to reply it, because we are. Please, Serena, do you mind unmuting yourself, because that's kind of a long question. And then I need either to give her permission to unmute herself.
Yeah, but please please unmute her because it's just a long. It's a long.
Quite big, yeah.
I'm sorry. Can you hear me?
Yes.
Yes.
Clear.
Okay, perfect. So I'm using this to like get surfaces and then calculate the real area that happens in my tribological concept for a further mathematical consideration for where. So I do it in that way that I'm using my surfaces and I'm converting them to 2D meshes, and then I'm calculating the highest points that are in contact. But I'm not sure if that's the smartest way to do it or if there are like any better ways for it. Probably.
Say, Francesca, did you copy that? I mean, one surface has this surface that I randomized. It had either 256 transversal or 256 longitudinal 2D profiles.
Mm-hmm.
So of course, neither one of those profiles will be Gaussian or Weibull in the way that I wanted them to be to begin with. So you have to do some average of 3D to 2D to preserve that.
Andreas, we lost you for 5 seconds, so do you mind repeating the last statement?
Okay, so I said you have to do some averaging. If you take the average profile, longitudinal profile over the whole surface, it will at least have the same height probability density, but it will the spectral content will look different. I mean that then you have to somehow control that. I'm not on a straight hand. I don't know exactly how to do it.
Okay. Yeah, I try to average it, but I'm still not sure if like the results that I'm getting are actually useful.
I'm actually, in terms of generation, I have modified the code. Well, not me, but a colleague has modified the code to be able to just generate profiles directly instead of generate surfaces and then average. It's basically the same procedure, just dealing with one dimension less.
Mm.
I'm not sure if that would help or not.
Probably, because I'm always trying to get like one dimension less for it. Yeah.
I mean, if you go as Andreas said, under the hood, it's basically sort of it's basically removing everything.
Not everything.
Okay.
Yeah, I mean, you can also. Yeah.
Thank you very much. I'll try to figure that out.
You can always easily reach them by email, Francesca, Andreas.
Yeah, exactly. That was I was going to say, that you can always reach by email, and that we can have a more calm discussion.
Thank you very much. That's really helpful.
With that, we are going to close this webinar. It's 4 o'clock, and thanks our presenters, thanks TriboNet team, audience. We see you in the next webinar. So have a good weekend, and well, just enjoy the weekend. We deserve it. Ciao.
Thank you. Thank you, Andreas. Thank you, Francesca.
Thank you for letting us have this show. All the best.
Thank you. Have a good weekend. Bye-bye.